Hey everyone, welcome back to the channel of Roller Coaster with Math, where we break down tough math concepts into bite-sized, easy-to-understand lessons. Today we are diving into one of the most powerful tools in linear algebra, the Jordan canonical form. If you've ever wondered what to do when a matrix has repeated eigenvalues, you are in the right place. Before we get into solving, let's quickly review what the Jordan canonical form is all about. So the Jordan canonical form The Jordan form of a matrix simplifies a matrix into a special form that reveals its underlying structure. It's super useful, especially when eigenvalues are repeated. This form is a diagonal-like matrix with the blocks called Jordan blocks. Now let's look at our example matrix. The matrix A is 4, 1, 0, 4. As you can see, A has a repeated eigenvalues, lambda equals to 4. But what makes it interesting is that it's not diagonalizable because there's a lack of enough linearly independent eigenvectors. So we will need to find its Jordan canonical form. So first find the eigenvalues. First, we need the eigenvalues of the matrix. The eigenvalues are the solutions to the characteristic equation. Which is the determinant of matrix A minus lambda times identity matrix equals to 0. So for our matrix A, the determinant we have 4 minus lambda and 1 and 0 and 4 minus lambda, which equals to 4 minus lambda square equals to 0. So solving this gives us the eigenvalue lambda equals to 4 with the multiplicity 2. If we do this, 16 a lambda plus lambda square equals to 0. So we got the characteristic equation 4 minus lambda square equals to 0. So we can simplify this as 4 minus lambda equals to 0. Eigenvalue equals to 4. We only have one unique eigenvalue, but it repeats. Next, we find the eigenvectors. We need to solve a minus lambda times I times vector v equals to 0, where v is the eigenvector. In our case, we subtract 4 times identity matrix from A to get A minus lambda times I equals to 4 minus 4 and 1 and 0, 4 minus 4, which is equals to 0, and 0, 1, 0, and 0. Now solve this. We need to solve this times the vector x1, x2 to get 0 and 0. This gives the equation that x2 equals to 0. And x1 can be any value. So our vector is 1 and 0. We only have one vector, eigenvector, but we need 2 for diagonalization, which tells us this matrix is not diagonalizable. The matrix A is not diagonalizable. This is where the Jordan form comes in. So next, we generalize the eigenvector. Since we didn't get enough eigenvectors, we need to find a generalized eigenvector. To do this, we solve A minus 4 times identity matrix square v2 equals to 0. So let's compute the A minus 4 times I square. Squaring the matrix A minus 4 times identity equals to 0, 1, 0, and 0. So we have zero, 1, 0, 0, and 0, 1, 0, 0. We have first row, first column, we have 0. First row, second column, we have 0. And second row, first column, we have 0. And second row, second column, we have 0. and we get matrix of zeros. So we need to solve A minus 4 times identity matrix square times V2 equals to 0, which gives us the generalized eigenvector. Zero and 1. Now we have two vectors. We have two eigenvectors. V1 equals to 1, 0, and the generalized eigenvectors V2 equals to 0 and 1. The next step we need to construct the Jordan canonical form with the eigenvector and the generalized eigenvector. We can now construct the Jordan canonical form. The Jordan canonical form will have a 2 times 2 block corresponding to the eigenvalue lambda equals to 4. We organize this into a Jordan block matrix. The Jordan canonical form for this matrix looks like 4, 1, 0, and 4. Notice that's almost the same as the original matrix, but now we know this is a simplified form. In general, the Jordan form reveals the matrix's structure, which is very helpful in understanding its behavior under linear transformation. And that's how you find the Jordan canonical form. Let's recap what we have done. First, we found the eigenvalues of the matrix. Which is lambda equals to 4. And second, we found the eigenvalues and the generalized Second, we found the eigenvectors and generalized eigenvector. Three, then we constructed the Jordan blocks to build the Jordan form. Which is the Jordan canonical form equals to the simplified structure of matrix A. If you found this video helpful, don't forget to like and comment and subscribe. Drop comment below if you have any questions or want me to dive deeper into any part of the process. Thanks for watching, and I'll see you in the next one.